Now that we know the basic setup for our partial fraction decompositions, I want to talk about how we solve for those arbitrary constants in the numerator. So there's two main methods that we can use. One of them is not always the best method over the other. That's why I'm going to show you both of them. Typically, I don't like showing two different methods for something, but in this case, it is going to be worthwhile to know both of them. So we're going to start back at the beginning of a problem just to get a little bit more practice with getting the basic setup. But we're not just going to stop there. We're going to continue through and we're going to solve for those constants. And it's a lot easier for me to show you with an example. We're not going to integrate yet. That's the last thing we're going to add to this. But we are going to use partial fraction decomposition. And one of the things I don't think I mentioned in the last video that's really, really important is that when you start these problems, you have to make sure you always start with a proper fraction. And what that means is that the degree in your denominator is larger than the degree in your numerator. If the degrees are equal, or if the degree in the numerator is larger, then we could do polynomial long division to simplify it first. So we always want to make sure of this before we start the partial fraction decomposition process. And I'll make sure that we see an example that has this, where we have to simplify first. So the first fraction we're going to look at, we will start with just a rational expression. We'll go through the basic setup for our partial fractions, and then we'll also solve for our numerators, but we'll try to start with a simple one. We're just going to decompose x minus 9 divided by x squared minus 3x minus 18. So remember, this always starts with factoring, but check to make sure that you are working with a proper fraction. So the degree in the numerator is 1, the degree in the denominator is 2. So this is a proper fraction because the degree in the denominator is larger, which is what we want. So once we check that, we can see how our denominator is going to factor. So remember, it's always going to factor into either linear or irreducible quadratics. Or we're looking for two numbers that multiply to be negative 18 and add to be negative 3. And that's going to be x minus 6, x plus 3. So we've got two linear factors. And when our denominators are linear, our numerators are 1 power smaller, which means our numerators are going to be constants. So this is about as far as we got in the last video. What we want to do now is talk about how to solve for the a and the b. And it can be a lot of tedious algebra. But what we have right now is that x minus 9 over, and I'm going to use the factored form, over x minus 6 times x plus 3 is equal to a over x minus 6 plus b over x plus 3. The very first thing that we are going to do in order to solve for the a and the b is clear the fractions. And we clear the fractions by multiplying through by the factored form of that original denominator. And I'm going to do the factored form just because it's going to be easier to see how things cancel. So mathematically, this is legal as long as we multiply everything by x minus 6 and x plus 3, as long as we multiply all the terms by it. So I'm going to multiply all three of my terms here by x minus 6 and x plus 3. So I'm going to multiply here, I'm going to multiply here, and I'm going to multiply here. And what we get when we do that, typically as you get more comfortable, you're not going to have to write down every single one of these steps. But what we would have is x minus 6, x plus 3, and then our original numerator there, x minus 9, all over x minus 6, x plus 3, equals, I'm going to go ahead and put my a first, a times x minus 6, x plus 3, over x minus 6, plus b, x minus 6, x plus 3, over x plus 3. So you see, all I've done is I've taken my original denominator and I've multiplied it by each of my fractions. And when you do that, it multiplies into the numerator. And that should clear all of our fractions. You should have common factors in all of your numerators and denominators that cancel each other out. So once we simplify, we're just left with x minus 9 equals a times x plus 3 plus b times x minus 6. Which looks a little bit nicer, but it still doesn't really look solvable. It's got three unknown values in it, x, a, and b. We want this partial fraction decomposition to work for every possible substitution for x, which means I should be able to plug anything I want in for x, and this should work. So there are some strategic values of x that we can plug in that will help us solve for a and for b. And those are values that make our original factors equal 0. So if I wanted to make this piece equal 0, what x value could I plug in? We're going to plug in x equals 6. So I'm going to go through that entire equation that I have left now, and I'm going to plug in x equals 6. So when I do that, I get 6 minus 9 is negative 3 equals a times 6 plus 3 is 9 plus b times 6 minus 6 is 0. So this was a strategic value because it completely got rid of the b variable for us. It also got rid of the x variable because we plugged in for the x variable. So now we're just left with the a to solve for. So I've got negative 3 equals 9a, and we just have to divide the 9 over. So a must be negative 1/3 when we simplify. That's not my answer, but I'm boxing it just so I can find it later. So we're going to do the same thing again, but this time I'm going to zero out my a term. So there's a specific x value I can plug in that will zero out a times x plus 3. And that's x equals negative 3. So I'm going to go through that entire equation again here and replace all my x's with negative 3's. On the left, I've got negative 3 minus 9, which is negative 12. A times negative 3 plus 3 is 0. And b times negative 3 minus 6 is negative 9. And the whole a term just zeroes out. And we replace the x's, so now we're just left with an equation that we can solve for b. So negative 12 equals negative 9b, which means b must be 4/3. So as long as all of our factors are linear, we should be able to just pick x values that will zero out all but one of them so that we could solve for one at a time. The reason that we have a second method that I'm going to show you in a few minutes is because we don't always have linear factors. Sometimes we're going to have irreducible quadratic factors that we cannot zero out just by plugging an x value in. So that's why we need the second method. So our partial fraction decomposition becomes a over x minus 6. Well, a was negative 1/3. So now I've got negative 1/3 over x minus 6 plus 4/3 over x plus 3. And I wouldn't worry about simplifying this complex fraction right now. We've got a fraction inside of a fraction. Our ultimate goal is going to be to integrate this. So when we do that, those numerators there, no matter whether they're whole numbers or fractions, they're just going to come out front as coefficients. So don't really waste any time trying to fix those complex fractions. It's fine to just leave them, because this is really just, this isn't our final answer. This is just an intermediate step from where we're ultimately trying to get to. So let's look at another one. This time we are going to try to find the partial fraction decomposition for 12x minus 8 over x cubed minus 2x squared. Make sure that you have a proper fraction, and my degree in the numerator is 1. My degree in the denominator is 3. Since the degree in the denominator is larger, it is a proper fraction, so we're safe to go ahead and continue with our partial fraction decomposition. If it was not proper, we would want to use polynomial division to simplify it and make it proper. So that means our next step is factoring. We want to factor out our denominator into linear or quadratic factors. So x cubed minus 2x squared, they have a common factor of x squared. And when I pull it out, I'm left with x minus 2. Now remember what we said in the last video, that x squared really is a repeated linear factor. So these are all linear factors, x times x times x minus 2, which means all of our numerators can be constants. So I'm going to start with my first factor, and because it's a repeated factor, I only start with one of them. And then I'm going to work my way up in power until that power matches what I actually have in my factorization. So I actually have an x squared in my factorization, so I can stop at the x squared. I don't have to say plus c over x cubed, because I don't have an x cubed there in my factorization, just x squared. And then I also have an x minus 2, which is linear, so that one also gets a constant numerator. So that's our basic setup. Now we want to rewrite this and do a whole bunch of algebra. When I rewrite this, I'm going to rewrite it with a factored denominator, just because it will be easier to see how things cancel. So remember, we're going to multiply through by the original denominator, which was x squared times x minus 2. And we now have 4 fractions that x squared times x minus 2 needs to be distributed to. When you distribute it to the original fraction, since that's the original denominator that we're multiplying by, it's always going to cancel the original denominator and just leave you with your numerator. When I multiply into my a over x, one of the x's will cancel, and I'll be left with a x minus 2. When I multiply into my b over x squared, the x squares will cancel. I'll be left with b times x minus 2. And then when I multiply into my c fraction, the x minus 2's cancel, so I'm left with cx squared. So if you look at those original two factors we had, those magic numbers that we're going to plug in for x are whatever make those equal 0. So we're going to use 0 for the x squared, and then we're going to use 2 for the x minus 2. Those will zero those out. So I'm going to go through and plug in x equals 0, and that should allow me to solve for one of my arbitrary constants in my numerators. So if I plug in x equals 0, and you're going to plug it in everywhere, including, don't forget about the left-hand side of this equation, which was the original fraction. If I plug in 0, I get negative 8 equals, well, this has a factor of x, so that whole thing's going to zero out. This has a factor of x, so that whole thing's going to zero out. All I'm going to be left with is b times 0 minus 2. So negative 8 equals negative 2b, which means b equals 4. Our other value we said we could plug in is 2. So if we plug 2 in everywhere for this equation, 2 times 12 is 24, minus 8 is 16. So on the left we get 16. Anything with a factor of x minus 2 is going to zero out. So this one zeroes out again, and this time this one zeroes out. So the a and the b are gone. But this time we can solve for the c. So I've got c times 2 squared. So 16 equals 4c, which means c has to also be 4. So we've reached a problem here. We've run out of numbers, magic numbers to plug in. I call them magic numbers because they make things zero out. We only identified 2 of them. We still have a third unknown numerator of a. So in order to solve for a, if you've already been able to solve for everything else, remember, we want this to work for every value of x. So what we can do, if you're out of magic numbers, is you can plug in any random x value, but we're also going to have to plug back in the b and the c that we found. That way b and c are not unknown values in this equation. So I'm going to be replacing all of the x's with 1. I'm also going to be plugging in my b equals 4 and my c equals 4. And that will make it so a is the only unknown value in this equation. We can solve for a. So we plug in 1, I get 12 minus 8 is 4. We don't know a, but I'm going to have a times 1 minus 2, plus my b value, which I've already solved and got 4. And then remember, we're plugging in x equals 1, so times 1 minus 2. And then my c value was 4 times 1 squared. A is the only unknown, so we can just do a little bit of quick algebra here and figure out a. So 1 minus 2 is negative 1. That just ends up as negative a minus 4 plus 4. So a equals negative 4. Which means our partial fraction decomposition is negative 4 over x plus 4 over x squared plus 4 over x minus 2. And when it comes time to integrate, this expression here is going to be much easier to integrate than the original expression that had cubes in it. We had a linear divided by a cubic. We have not learned any other method yet to help us integrate that. It's not a sum or difference of squares. It's not going to work with U substitution. So anytime that you've got a rational expression and your denominator is factorable, we can always break it apart into these nice simple fractions that are going to integrate really easily. So finally, I want to show you one that has an irreducible quadratic, because this one we're going to have to do a little bit differently. So for this last one, we are going to try to figure out the partial fraction decomposition for x plus 5 over x cubed plus 9x. Now this is a proper fraction, so our first step is going to be to factor our denominator, and those two terms just have a common factor of x. When we pull it out, we're left with x squared plus 9, which is an irreducible quadratic. We can't factor x squared plus 9 any further. So our basic setup for a partial fraction decomposition, we're going to have one fraction for each of our factors. The linear factor, remember, the numerators are always going to be one power smaller than the denominators. So the linear factor is going to have a constant numerator. The quadratic factor is going to have a linear numerator. And a basic linear expression would be bx plus c. I'm using b and c just because I wrote it second. If I wrote it first, it could be ax plus b. The order of those is really arbitrary. Now, we need to multiply through by the original denominator to clear the fractions. Once the fractions are cleared, we can start solving. So remember, this is your original denominator. So when we multiply by the original fraction, it's going to completely cancel it out, and we'll just be left with our numerator. When we distribute to our a fraction, the x's will cancel, and we'll be left with a times x squared plus 9. And then when we distribute to the bx plus c fraction, the x squared plus 9's cancel, and we're left with x times bx plus c. So for this one, I'm going to show you the second possible solution method. There aren't really magic numbers here. We could technically plug in x equals 0. That would help us out to solve for the a. But then there's nothing we can plug in to zero out the a, and then there's still two unknowns in the second part of our partial fraction decomposition. So the other option for solving, and then sometimes you can use a combination of the two methods, the other option is to just get everything multiplied out and match up like terms on both sides of your equation. So I've got x plus 5 equals ax squared plus 9a plus bx squared plus cx. What I'm going to do is I'm going to compare terms on the left side of the equation and on the right side of the equation. And right now it says they're equal, which means all my like terms should match. So sometimes we need to do this in a list because sometimes it creates a system of equations that we need to solve. So looking through this entire equation, the largest power I see is a squared. So I'm going to compare my x squared terms. So on the left, I don't have any of them. So I'm going to say 0 equals. On the right, I've got a plus b of them. So far what we know is that a plus b has to equal 0. And then let's compare our linear terms, our x terms. On the left, I have one of them. On the right, I have c of them. So perfect, we've got the c value, c equals 1. And then if you look at your constant terms, on the left and the right, the constant on the left is a 5. The constant on the right, sometimes it's hard to identify. Remember, the only variable here is the x. The a, b, c are arbitrary constants. So the piece without the x is right here, 9a. We can solve that equation for a. It's only got one unknown in it. So this is going to lead us to a equals 5/9. Well, if a is 5/9, we could use that to solve for b. because a plus b has to be 0. That means b has to be negative 5/9. So the second method just involves getting the right-hand side all multiplied out and then matching up like terms on the left-hand side and the right-hand side. Notice I left the variables out of these equations. All I'm doing is matching up coefficients. So the coefficient of the x squared on the left was 0 because we didn't have any. And the coefficients for the x squared on the right were a and b. A plus b. And then I looked at my linear terms. The linear term on the left had a coefficient of 1. I only had one linear term on the right, and it had a coefficient of c. That means c has to equal 1 if it's true that the left-hand side equals the right-hand side. And then the same way we matched up the constants. So we are able to figure out a, b, and c this way as well, and we haven't plugged anything in for x. So now we've got a over x, so our a was 5/9. And remember, don't worry about simplifying this complex fraction, because our ultimate goal is going to be to integrate. And then we've got bx plus c over x squared plus 9. So our b is negative 5/9. And then our c was 1. So there's our bx plus c over x squared plus 9. That is our partial fraction decomposition. Believe it or not, this is easier than the original that we started with. It might look a little bit more complicated. Our ultimate goal is to integrate. This definitely is easier to integrate. That's just going to turn into a log. And then usually when we have these irreducible quadratics, we're going to have to split this apart into two separate fractions and deal with them individually. So you're typically, when we come to the integration step, we're actually going to work with it as 5/9 over x plus negative 5/9, and you could change that to minus if you want, negative 5/9 x over x squared plus 9 plus 1 over x squared plus 9. So all I did there was I separated the terms in my numerator. And this is definitely going to be a lot easier to integrate because this one's just going to turn into a log. This one we can do a u substitution. This one turns into arctangent.